everyone, and welcome to another quantum matter meets math session. Today we have the enormous pleasure of having Professor Xiao-Gang Wen with us. I am certain most of you know Xiao-Gang for his work, but I will attempt to give a short introduction anyways. Xiao-Gang Wen had his Bachelor in Science from the University of Science and Technology of China in 1982 and PhD in Physics from Princeton in 1987. He studied superstring theory under the supervision of Edward Wheaton at Princeton. Later, from 1987 to 1989, he changed to condensed matter physics while working in collaboration with Robert Schrieffer, Frank Wilczek, and Anthony Z at the Institute for Theoretical Physics, University of California, Santa Barbara. Xiao-Gang became a 5-year member of Institute for Advanced Study at Princeton in 1989 and joined MIT in 1991. Xiao-Gang is a Cecil and Ida Green Professor of Physics at MIT from 2004 to the present date, a Distinguished Moore Scholar at Caltech 2006, and a Distinguished Research Chair at Perimeter Institute 2009. Among other honors, Wen is a Sloan Foundation Fellow 2011, co-winner of the Oliver Ellsworth Buckley Condensed Matter Physics Prize from 2017 for theories of topological order and its consequences in a broad range of physical systems. Was elected to National Academy of Science in 2018 in recognition of distinguished and continuing achievements in original research, and he was awarded the 2018 Dirac Medal by the ICTP jointly with Dantan Son and Sudhir Sachdev for his contribution towards understanding novel phases in strongly interacting many-body systems, introducing original transdisciplinary techniques. It is truly an honor to have Professor Xiao-Gang Wen here with us, even if not physically, but virtually. Today, he will tell us about a holographic view of symmetry, symmetry as shadow of topological order. So without further ado, I leave you with Xiao-Gang. Please.
Thank you very much for this kind introduction. Yeah, it's really my great pleasure to give this talk. And today I will mainly talk about a new point of view of symmetry and its relation with a strongly correlated gapless system. So we know that at 0 temperature, we may have 3 kinds of quantum matter. And the first kind is the one with the energy gap, like insulator, superconductor. So all the excitations have an energy gap. So therefore, at a low energy, we may say these states are trivial. And there's another second kind we call simple, because at a low energy, there's a few low energy mode, like a silver fluid and like a crystal, you have sound wave. And the third kind is more complicated, is actually Fermi liquid. You know, the topological order belong to this trivial class because they have an energy gap. And so we have a very good systematic understanding of this class of states. Okay, since the last 30 years of development. And so the next big question is to gain a systematic understanding of a gapless quantum state matter. Okay, and which is much more difficult. And the most gapless quantum matter we studied, like a Fermi liquid or something like that, have the property that at the low energy, we have non-interacting excitations. But we also have gapless states, most of them, whose low energy excitation are not non-interacting, have a strong interaction. So we call them strongly correlated gapless states. They have no quasi-particles. And for those kind of gapless states, it's very hard to understand them. So they usually appear at a quantum critical point, you know, at the phase transition. And so this is maybe our main motivation, how to understand these simple gapless states. And here I want to explain that the simple and the complicated really means that the simple means there's only a few a linear mode, means frequency proportional momentum. So there's a linear dispersion relation. And the complicated, like a Fermi liquid, actually from field theory point of view, you have to use a field theory with an infinite number of field to describe them. So actually, although in solid state physics, we usually talk about Fermi liquid first, but actually, theoretically, they are most complicated system. And I recently wrote a paper on this infinite number of field effective theory. Okay. So here, let me just discuss an example. This is a transverse field Ising model. As they are the example of a strongly correlated gapless states. Okay. And the model is very simple. And we have a spin live on the vertex. So I have a spin up, a spin down, and etc. Okay. And so we have operator act on a spin, like this Pauli spin Z operator, Pauling spin X operator. Okay. So this is just a transverse Ising model. And this J term describe a nearest neighbor spin-spin interaction, and H term describe interaction with external magnetic field pointing in X direction. Okay. And there is also a Z2 global symmetry, which also emphasizes on-side symmetry, means that the symmetry action is on each spin on each side. And then the tensor product of those symmetry action gave us a total symmetry action, which is just a spin flip. This symmetry action is spin flip. Okay. And in this talk, we'll restrict ourselves in a symmetric sub-Hilbert space under this transformation. And so we'll see why this is important later. Okay. So this is the model. And this model, there is a critical point when H equal to J. When H equal to J, there's a critical point. Okay. And so let's consider a limit where H is much bigger than J. So at a very strong field in X direction, so all the spin in pointing X direction, that's the ground states. Then as we lower the H, then this spin flip may become an excitation and became available. And then when H getting smaller and smaller, we have more and more spin flip. Okay. So here, the spin flip have a property that a two spin flip can annihilate, became trivial. So this corresponds to this mode 2 conservation of a spin flip, and that's also a consequence of this Z2 symmetry. Okay. So from here, we see that we have a phase transition. That's for large H, we have a Z2 symmetric state. For small h, we have so many spin flip, they condense. The condensation of spin flip gave us a Z2 symmetry breaking states. And the transition point is a critical point we call the Ising critical point. And this Ising critical point, is an example where it's kind of strongly correlated. It's not like superfluid to have a bosonic mode, Okay. So, however, there's another point of view of Ising critical point, which is really the main topic of this talk. That is, we can start with the symmetry breaking states. Okay, but we still restrict ourselves in the symmetric subspace. So that means we consider the O up plus O down. This superposition belong to this symmetric subspace. Okay. So this is a ground state, O up plus O down. And then what are the excitations? Excitation domain words, we can flip a spin a segment, then plus this spin flip partners. Okay. So from here we see that there's two domain words. Okay. And these two domain work also have this fusion rule. Two domain work annihilate became nothing when they get close to each other. Okay. So therefore, from here you can see that a mode 2 conservation of a domain work also gave us a Z2 symmetry. and which we call the dual Z2 symmetry. And this is one of a main player of this talk. So we have a dual Z2 symmetry. It's really conservation of a domain wall. And then this is the picture in a large GA limit, in GA much bigger than H limit. But when H getting bigger, we have more and more domain wall. Eventually, we have too much domain wall, and domain wall condense, which break this dual Z2 symmetry. Okay. And then we have a critical point, which is a symmetry breaking of this dual Z2 symmetry. Okay. So that's a two-point view to understand the same critical point. I think we only have one critical point. So this critical point and the previous critical point is happen to coincide. You have a two different view. So if you combine these two-point view, we get this picture. If you look at the symmetry, well, we have a symmetric phase at a large h, symmetry breaking phase at small h. However, if you look at the dual symmetry, we have a symmetric phase in small h and a symmetry breaking phase in large h. But at the critical point, we can see that this critical point touch both symmetric region. So the critical point have both symmetry. That is one point. Because they touch this Z2 tilt symmetric one, so they have Z2 tilt symmetric symmetry. And they also touch Z2 symmetric, so they also have Z2 symmetry. So it's very tempting to put two symmetry together. We say that the critical point have both Z2 and Z2 tilt symmetry. Yeah, that's one point. Okay. So it's a in some sense this is not really surprising, because usually the critical point have an emerging symmetry, have a small symmetry. Yeah, so I have some larger symmetry. And in putting the two symmetry together, we call them a categorical symmetry. And there's a reason to call this, And the reason we call this categorical symmetry is that these two symmetry are not that independent. It's not like a translation symmetry and a spin flip symmetry. They are two independent symmetry. These two symmetry have a very special relation. And actually, they have so-called mutual statistics between them, for lack of a good word. So let me just call them mutual statistics. They have mutual statistics between them. And so there's a very special relation between these two, symmetry and a dual symmetry. Okay. So what is a mutual statistics? To really see these mutual statistics, okay, and also to write down the symmetry transformation within the symmetric subspace, we introduce this patch symmetry transformation. Okay, and within the symmetric subspace, the symmetry transformation would act trivially, because the symmetric subspace means the space which invariant and the symmetry transformation means the symmetry would act trivially. So we don't see symmetry transformation anymore. So within the symmetric subspace, to see the symmetry transformation, then we find a trick. We only transform the symmetry on the patch, say on the segment, say from just in the region from I1 to I2. So on this segment. And for the Z2 symmetry, for example, we just do the spin flip over this segment. Okay, and that's enough to define the symmetry, because this so-called symmetric local operator is operator which are invariant, which are commute with the symmetry transformation. But however, with the condition that this operator is at I, and their location I is far away from these two endpoint. Okay. As long as I is far away from the endpoint, then this commutation relation would put a constraint on this operator, and this gave us so-called symmetric local operator. And the symmetric Hamiltonian are simply the summation of this symmetric local operator. So that's allow us to define what do you mean by the symmetric Hamiltonian, because the symmetric Hamiltonian do not commute with this patch operator. But however, because Hamiltonian is a sum of local operator, each of a local operator commute with the patch operator as long as they far away from the endpoint. Yeah. So this is we really feel this is a better way to look at the symmetry. We really utilize the locality of Hamiltonian. In the many-body system, we have a local short-range interacting Hamiltonian, and this definition really utilizes that important feature. Okay, so this is the patch symmetry transformation for the Z2. And for the dual symmetry, then we need to go to the dual representation of the Ising model. In the dual representation of the Ising model, we have a spins or dual spin live on the link. So now the dual spin live on the link. So X tilt is described by this operator. Okay, so dual spin would live on the link, and then this and we can translate or transform this Ising model with the spin live on the site to Ising model with the spin live on the link, and then the operator act on the spin on the site like Xi became a pair of operator which act on spin on the link, and the original ZZ interaction became a single operator on the spin on the link. So this is a transformation, and then we get this dual Ising model, which actually have the same form as the original Ising model. Okay, and in this dual Ising model, it's clear we can see that this Z2 tilt symmetry is generated by this Z tilt operator, which commute with both Z term and this XX term. Okay, and again we have a patch operator which only act on the segment. Okay, and then now we can see that the original this Z2 symmetry operator is a product of X, now became product of X tilt and X tilt on the neighboring site. But however, when you have a product of H, the internal X tilt all cancel each other. So at the end, the patch operator became a 2X tilt on the end of the patch, but the middle is empty. There's empty bulk. Yeah, there's trivial bulk. Okay, so in some sense that means any local operator in the dual model will commute with this patch operator, and this is expected. Actually, any local operator in the dual model actually is allowed have original Z2 symmetry. It's allowed by the original Z2 symmetry. Okay, so this is a so this is the explicit representation of these two symmetry. So to summarize that, we have transverse Ising model, we have the Z2 symmetry, but however the dual Z2 symmetry, which is given by this, will written in terms of original Ising model became the patch operator became 2Z and 2N. Again, there's an empty bulk, trivial bulk. Yeah, please go ahead.
Yes, I was wondering if it is possible to recast this as the action of a groupoid with base the real line parameterized by the quotient H over J or something like that.
Yeah, I'm sorry, I'm not familiar with the groupoid language, but I want to say that yeah, this language probably really close to this operator algebra, this maybe Van Neumann algebra, those kind of things, and okay. So I have this so basically we try to define the operator algebra of so-called local symmetric operators, and how to put these constraints from our operator algebra point of view, But I'm not familiar with operator algebra, so I probably I couldn't really describe in that way. But I'm learning, I recent months I'm trying to learn that, and hopefully I can recast all this in the operator algebra point of view. Yeah.
Okay.
So
Okay.
in terms of operator algebra, I basically say that these two symmetry basically define the same operator algebra. You know, then the dual model and the original model, they just the same different representation of same operator algebra, and the operator algebra will determine everything. Yeah.
Okay. Thank you.
Yeah. And but however, in the dual Ising model, we have these two patch symmetry operator, but now the original Z2 symmetry became empty bulk, but the Z2 dual symmetry, you know, seems non-trivial in the bulk. Okay. And so the point is that the so-called local symmetric operator, which commute with both of them, really are equivalent. Basically, I would try to say that these two set of operator, the commutant, really are equivalent, they are same operator algebra. So they really define the same thing. They are equivalent. Okay. And but they have it's kind of very different way to view these two symmetry. Okay. And here we notice that this Z operator actually is a creation of a Z2 charge. So this operator is a creation of a charge of this symmetry transformation because the Z do not commute with this product of X. Okay. And so similarly, this X tilde operator create a charge of this Z tilde. So and vice versa actually. So basically, the point is that the endpoint of one symmetry operator corresponds to charge of the other dual symmetry. Okay. And why this is important, really, because of the following. In physics, when we say that symmetry breaking, when we say the symmetry breaking, like this, I mean, let's call this Z2 symmetry breaking, then that really means that this charge would be constant. Okay. Okay. I'm sorry. Let me say that again. So we have Z2 tilde symmetry. Okay. Then we know that the patch operator of Z2 symmetry actually is a correlation of all the parameter of the dual symmetry. Okay. Because the patch operator of the Z2 symmetry create a pair of dual symmetry charge at its two ends. Okay. So therefore, when we have this dual symmetry breaking, spontaneous symmetry breaking, that means their charge operator will have a constant correlation. So this really means the charge operator at x1, charge operator at x2, they have a constant correlation, and that means the symmetry breaking. Okay. And however, in the dual symmetry symmetric phase, then this operator would have a exponential decay. That means the symmetric phase. Okay. And then this then at the critical point, what we have is that the both correlation function of these two operators have algebraic decay. They are not like a constant. Both of them are not constant. So they don't have a long range order. Okay. So that means that both these Z2 charge, we call this E, and the domain wall we call M. Both those excitations are not condensed. So we have this critical point. They are not condensed, means the symmetry is not broken, and so this really a way to understand why this this is not broken. Okay. And it turns out that these two symmetry is correlated because there's a following theorem proved by Levin. That is these two symmetry in a gapped phase. So these two phases are gapped, and one of the symmetry must be broken. You know, a state with unbroken. If both symmetry are not broken, this state must be gapless. A gap state must break one of the symmetry. That's their relation. But why they have such a property of these two symmetry? Really because they do not commute. This is something like to say. And so let me draw this more clearly. So we have this I1 and I2. That is a wonderful symmetry, like a Z2 symmetry. Okay. Then we have this J1 and J2 arranged this way. And then that's a patch operator of Z2 dual symmetry. If they arrange this way, these two operators anti-commute with a minus sign. Certainly, if two segments do not overlap, they commute, certainly. If one operator are within another operator, then they also commute. But they have this kind of overlap. If they have this kind of overlap, they anti-commute. And this is a special property. That's what we call mutual statistics. Yeah, this is what we call mutual statistics. So they have this very, very special relation. So because these two Z2 symmetry is very normal. But however, to have this very special relation, when two Z2 symmetry have this very special relation, they have this consequence. That is a gapped state must break one of the symmetry. If both symmetry are not broken, the state must be gapless. So they all come from this mutual statistics, coming from this very special relation. Okay. So this is why this became interesting now. So because as I mentioned that the gapless state is very hard to understand. First thing, we don't even have a proper name for them. We just call them A, B, and C, you know. we lack of insight and we don't have a proper name. Now we see that, well, this gapless state may be related to symmetry with the mutual statistics. Maybe this is general feature. Maybe every gapless state have this feature. Then this kind of symmetry with the non-trivial mutual statistics can be used as a label or maybe classify the gapless states. That may not be true, but at the moment we don't have anything, so anything will be good. So this is a kind of a situation. So right now we try to entertain ourselves. Can this symmetry with non-trivial mutual statistics have very strong close tie to gapless states, and it can be viewed as a natural label for gapless states? If that is true, then we can use this kind of symmetry to systematically study gapless states. And so that's why we gave this symmetry a special name called the categorical symmetry. That's why we try to emphasize those kind of symmetry are important. The categorical symmetry have this kind of non-trivial mutual statistics, which may have a close tie to gapless states. That is a motivation. Okay, so so this is what we just mentioned, that the gapless states are really very special. As I mentioned that the most, not most, at least, okay, most of gapless states in the textbook are very special one. They are gapless states with a low energy excitation which are non-interacting. We call it quasi-particle. But in nature, the more generic gapless states, where the low energy excitation always interact. So they always have interaction. But in physics, when things have interaction, there's tendency to open up energy gap. To have interaction without opening energy gap, that means interaction has to have a perfect balance. Very strange, very, very special arrangement. So those particles keep interacting, but they remain at a low energy. They are not pushed to the high energy. And this is a very, very special interaction. And I emphasize this is a very special kind of interaction are reflected by this emergent symmetry. And here we emphasize that this emergent symmetry may have a non-trivial mutual statistics, and we call them categorical symmetry. Yeah, the wish is that this categorical symmetry probably can help us to understand the gapless states. Yeah. And to really make that point, and also to have a deeper understanding of categorical symmetry, to understand why we have a mutual statistics, what that really means. Okay. Then we go to one of a main topic of this talk, that is a holographic point of view. Is that we realize that the categorical symmetry actually live in one higher dimension. It's it should remind me this prisoner K. Yeah, I think we all know a story that if the prisoner who can only see the shadow on the wall, and they think everything is like a shadow, and but when you look enough shadow, hopefully one of the prisoner may realize, wow, those different shadows are related, and they actually is a projection of something we never seen before. So the shadow are related means they're mutual statistics. So actually they may come from something in one higher dimension. So the symmetry and the dual symmetry are just two different projections of same object. So this is how they are related. And so this is the story. So how to understand, how to see this story? Well, let's go to one higher dimension. The Ising model in 1+1 dimension, one dimension space, one dimension time. So we go to one higher dimension, we have 2+1 dimension, means 2-dimensional space, 1-dimension time. And we consider 2+1 dimension Z2 gate theory. Okay, yeah, this is something new player, the Z2 gate theory. This Z2 gate theory have a so-called this Z2 charge. Gauge field have a gauge charge, and the gauge charge are Z2 representation. So we have this Z2 charge, which are boson. As a gauge theory, we have also flux, gauge flux. And for the Z2 group, the flux is just a pi holonomy. You go around a point, you get a pi flux. So this pi flux is called M excitation. So that's a basic excitation in the Z2 gate theory. You may have also trivial one, and we have a Z2 charge, Z2 flux, and their bound states. The bound state of Z2 charge and Z2 flux is called F. And this F actually is a fermion, because Z2 charge, Z2 flux have a non-trivial mutual statistics. If you move Z2 charge around Z2 flux, then you have a phase change of pi. So they have a non-trivial mutual statistics. And so although each of them are boson, the bound state these two boson with non-trivial mutual statistics give us a fermion. So this is kind of magic of a fractional statistics. Okay. And so this is a 4 elementary excitation in the Z2 gauge theory. Okay. And then the Z2 gauge theory have a boundary. And one of boundary is obtained by condensing the Z2 vortex, Z2 flux. And we condense Z2 flux, and that's one way to get a boundary. Okay. And then when this vortex condense the boundary, then we get but this Z2 charge E is not condensed. So then we have, so this boundary would have this excitation E. Okay. And this is exactly the correspond to what we talk about, that the mode 2 conservation. Yeah, I didn't mention, I did not mention this. This M also have a mode 2 fusion rule. And the E also have a same mode 2 fusion rule. So this mode 2 fusion rule, this give us this Z2, and the mode 2 conservation of M flux give us a Z2 tilt. Okay. So when this M condense, and that is Z2 symmetry breaking. Yeah. But the E is not condensed, so that means Z2 is not broken. So you can see in the bulk, we have a 2Z2 symmetry. But the boundary, we have to condense something on the boundary. So the boundary break one of them and leave another unbroken. And that seems the picture we just discussed. So in a sense, the boundary of the Z2 gate theory can simulate this Ising model picture we just discussed. And actually, I don't know the audience. And this picture, I describe this picture in the physics way. And there's a mathematical way to describe this. Actually, in the mathematical describe this is that this 2 plus 1 dimensional theory is a braid fusion category. It's a Z2 quantum double. And then the boundary is a fusion category. And their relation is that the dream field center for boundary gave rise to the braid fusion category in the bulk. So that is a category language. So I did not use that language. And this in the braid fusion category, there's condensable algebra. For every condensed algebra, you can condense something to get a fusion category, which is a gapped boundary. Who the dream field center would recover itself? There's so whole thing have a very nice mathematical categorical way to describing this. But I'm not using that language. And but for those who are familiar with category theory, this is just that picture. And certainly for this Z2 gate theory, this M form a condensable algebra they can condense. Actually, E also form a condensable algebra they can condense. And so we can have another boundary which has E condensation, and which give us this Z2 symmetry breaking phase, but the dual symmetry symmetric. So give another phase. Yeah, please go on. Please.
Yes, I'm sorry. So in the example of the Ising model that you described, this Ising model you described,
yes.
What is this two-dimensional space and what is represented by the boundary?
Okay, it's the following. This two-dimensional space is something we just introduced, just something extra. And then what I try to claim that the boundary of this two-dimensional system behave like Ising model. So therefore, Ising model can be viewed as a boundary for 2D system. And this is a way, and this way we can understand this symmetry, dual symmetry more easily. Because the 2D model have a two symmetry. There's from E fusion rule and M fusion have the two symmetry explicitly. And the boundary became tricky because to have a boundary, we have to condense something. And so one of the symmetry must be spontaneously broken. And that's how we understand this, this kind of a strange result. Why a gap state must break one of the symmetry. Because from category point of view, the gap of the boundary must condense something. There's a condensable algebra in the bulk, and something condensed give you a gap the boundary. Okay, so the gap the phase on the boundary must break some symmetry because it must condense something. Yeah. However, if you do not condense anything, the boundary without condensation anything must be gapless. Okay,
thank you.
Yeah, but this is maybe more insight because in category theory in mathematics, people study systematically those condensable algebra, how they produce a fusion category, which actually describe a boundary, and how the dream field center fusion category give you a bulk category, and those kind of things they study. But the insight from physics to math is that if you do not condense anything, you get something new, which is a gapless boundary, which is beyond the category, because category always describe there's a gapped excitation, their fusion rule, their braiding, that's always gapped. The gapless boundary, gapless system is much more delicate than category theory, something else. So this really says that the dream field center for fusion category can be generalized as a dream field center of something gapless, who also gave rise to the braid fusion category in the bulk, and so the impact is mutual. So right now we learn, it's very painful to learn category theory, but we have to understand those entanglement, topological order, etc. And but from physics, there's insight, something not thought about by mathematicians probably the physics can suggest, yeah, those things may have connections. So maybe there's a bigger picture. Yeah. So this is So from here we can, so we have a different way to view the Ising model. So this is a Z2 spontaneous symmetry breaking, and this boundary is a E condense. That is a Z2 tilt, this dual symmetry, spontaneous symmetry breaking. So that's a two-phase of Ising model we are talking about. One is a M condensation, another is E condensation. And then the phase transition from this picture to that picture is a critical point we talk about where nothing condense. Yeah. And nothing condense is a gapless critical point between these two boundary phases. So we have two different boundary due to different condensation. The boundary phase transition is a nothing condense, that's a critical point. Okay. So this is really the key point. That's maybe we should view this this categorical symmetry as a topological order in one higher dimension. So this picture topological order in higher dimension itself is a categorical symmetry. Okay, and then we should view this the constraint the system with a categorical symmetry actually is a boundary of this topological order. And then the categorical symmetry may break in different way. You get different gap boundary. If they do not break, then you have a gapless boundary. So from here we can see that the gapless system basically is a boundary of a topological order in one higher dimension where nothing condense. So from here you can see that there's a close connection between gapless states and a topological order in one higher dimension. If nothing condense, you may have some gapless states. And then we can use a topological order in one higher dimension to label different gapless states. Or we can, another way is you can use a categorical symmetry to label different gapless states. So this is kind of a picture we try to push. Yes. Please.
Can I have a stupid question?
Yeah.
You have the similar picture where you have the gapless Dirac fermion on the boundary of Ti from this
yes
argument.
That's one, but there's a difference. For topological insulator, the boundary is indeed a gapless, can be gapless. But however, that's a really non-interacting picture. And when you have an interaction, let me see what I try to say. Actually, there are some resemblance, because if you in the example just mentioned, if you break this symmetry, like for Ti, there's a U1 rotation symmetry, U1 conservation symmetry, and the time roll symmetry. So if you break time roll symmetry, the boundary can be gapped. If no symmetry is broken, the boundary must be gapless. And in this aspect, there's some resemblance. And the difference is that for the Ti example, the bulk have a symmetry. The bulk have a U1 and a time reversal symmetry. And the boundary also have the same symmetry. And here, the bulk is a topological order. The bulk don't have symmetry. Bulk just have entanglement. This is some kind of a entangled system, have a topological order. The bulk Hamiltonian have no symmetry at all. But however, the bulk have a topological excitation that have emergent symmetry in the bulk. And this emergent symmetry became the Z2 symmetry or Z2 dual symmetry on the boundary we talk about. Yeah.
Thank you.
So this is really, so there's some resemblance, but also there's some difference. Yeah. And actually, this is maybe the main picture, the main result of this talk is that it's really this picture. Okay. And so from this picture, what you really say that the categorical symmetry is just another name for topological order in one higher dimension. These two are really the same thing, you know. And when you say a system have a categorical symmetry, it's the same as to say we have a topological order in one higher dimension, and we consider it a boundary. the system we refer to actually the boundary of a topological order in one higher dimension. And these two are equivalent. So when you implement a categorical symmetry, it's really like a study a boundary of a topological order in one higher dimension. For different categorical symmetry, you have different topological order. Yeah, so that is the point. So now using the remaining maybe 10 minutes or so, I'll try to explain in more detail how categorical symmetry can determine gapless states, how that can be achieved. Okay, and so the point is that we need a data to describe a categorical symmetry, means we need data to describe a 2+1 topological order, the topological order in one higher dimension. We also need the data to describe 1+1D gapless states. Then we ask how these two data are related. So then that tells us how one data determine the other. So that is that's what we try to say. And then the data to describe a topological order in 2+ dimension, we can use so-called wave function overlap. Okay, so that's one thing we know that for the topological order on the torus, we have degenerate ground states. So the degenerate ground state labeled by this alpha and beta. Okay, so that's the degenerate ground states. Okay. Then we can consider this kind of overlap, like we can do the 90-degree rotation. So we have this a wave function alpha, and overlap with another wave function, but rotated by 90 degree. Okay. So then we get this wave function overlap with after 90-degree rotation give us so-called S matrix. Okay, they have some kind of matrix. The dimension is this degeneracy. And we can also do this another Dane twist. This from here to here is a Dane twist, and this is a 90-degree rotation. Okay, Dane twist is like a shear deformation. So again, we have a wave function, one wave function, overlapping with another wave function, but the other wave function have this kind of coordinate transformation, have some Dane twist, have some shear deformation. And those overlap are very tiny. Or actually, the wave function overlap is exponentially small as the system size getting bigger and bigger. They become smaller and smaller, very tiny overlap. But however, it's like a topological intangling entropy. If we remove this area law part, and there's a part do not depend on area, and we conjecture that this part is universal, actually. So this we call this ST matrix of this wave function. And this ST matrix form a modular transformation of a mapping class group of a torus. So this became a mathematics. So therefore, the modular transformation, so we can from the topological order, we can get the modular transformation. And this modular transformation happen to be the same as the modular transformation in this so-called Brady diffusion category. In the Brady diffusion category, there's also modular transformation. And that modular transformation and this modular transformation are related. So that's also relation of a topological order in 2+1 dimension are described by Brady diffusion category. That's a wonderful relation. So therefore, this representation for mapping class group of a modular transformation is a data for topological order. So that is one thing. Okay, and I think let me skip this. And but how do we understand we have a different degenerate ground states on torus? Okay. Well, one way to understand it is the following. So here I draw a torus. The surface of the solid cylinder is our space, and so we have a ground state on the surface of this cylinder. And then we fill the cylinder and imagine the radial direction, time direction. So it's like a universe, and we have a big bang at the center. So we start from nothing. Then our universe expand and become a torus. Then on the surface, we get a ground state. This time evolution gave us ground states. Okay. However, we can consider another time evolution. That is, we insert a word line for anion, some topological excitation word line for anion in the process. So we create an anion, then move them around, then annihilate. So let me use it. So this is the way to we can create a pair of anion, then move them all the way around the universe and then annihilate them. Okay, so but the anion never come to the surface. Okay. So when the time evolution involves such anions, then there's different time evolution, which give us different state on the surface. That's how we understand different ground states. They really correspond to different anions. So actually, there is a one-to-one correspondence between the anion types and the ground state degeneracy on the torus. Okay. So so this is how we understand the ground degeneracy. And from this picture, we can go on to discuss what is data to describe one plastic gapless states. What is data to describe one plastic gapless states? And usually in 1 + 1 dimensional gapless states, we consider the partition function. Okay, we consider the partition function. So partition function usually just a trace of e to the minus beta h. But here we include the translation in space by momentum operator. So we have this shear deformation translation in the space. Okay, and then this combination of time and spatial translation is called tau. So this parameter is tau. Okay, and then this usually in 1 + 1 dimensional system for gapless system, you have a non-trivial partition function, which have a modular transformation. Again, come back to modular transformation T and S. They are modular invariant. They are invariant and the mapping class group of a torus. This torus is space-time. So this partition function can be viewed as partition function on this 1 + 1D space-time. And then this modular transformation is a reparameterization of space-time which do not change partition function. So this 1 + 1D system have a modular invariant partition function. Okay. But however, this is not what we are after. Remember, we consider boundary for 2D topological order. So we have this picture. We have a topological order in 2 dimensions. We have this boundary. We want to study gapless boundary. What is a gapless boundary here? But now we have something new from the picture we have before. Because in the bulk, we have option to insert anions. We may have no anions, then we get one boundary partition function. We can insert some anions, then we can get a different boundary partition function. Actually, the different components of boundary partition function are equal to the number of anion type. It's same as the ground state degeneracy we talk about. Okay, so this is a key point that the boundary of topological order, their gapless states are described by partition function, but not one partition function, but several. That's a key. Several partition function, and each partition function are labeled by this anion type in the bulk. And also different partition function correspond to the ground state degeneracy we talk about here, because ground state degeneracy also are related to the anion type. They're all related. Okay. Then it's not so at this stage, it's not too hard to see that actually this multi-component partition function, they are not modular invariant, but modular covariant. That is under modular transformation, they transform by some kind of unitary matrix, S and T. And this ST matrix is data to characterize gapless boundary. The gapless boundary have a multi-component partition function, and the multi-component partition function is characterized by their modular transformation property described by this S and T matrix. Okay, so from here we see that the relation between two data is that the modular transformation matrix S and T matrix describing boundary partition function and the ST matrix describing bulk topological order, they are equal. Yeah, this is the insight here. They are equal. And so therefore, if you know the bulk topological order, we know their ST matrix, then we know how boundary partition function transform under similar modular transformation by same ST matrix. Okay. So this is from here, we can try to determine the partition function. Okay. So we know the boundary partition function transform in this way, where these ST matrix are given by the bulk topological order. Then from these two formula, we hope to determine partition function completely. And that seems hard because the partition function, those are discrete relation, not differential equation. How it seems impossible. But in one plus dimension, we know that for one plus dimension conformal field theory, their partition function is have this holomorphic decomposition with a finite component. It's a product of a holomorph function and anti-holomorph function with a finite sum. So that makes things not discrete. Holomorph function is very rigid. So using these insights, and we can determine using this equation to determine the partition function to a large degree. And this holomorph function is called conformal characters. And we have this a big table of all kinds of conformal character. So we can use those table assemble some partition function and check which assembling gave rise to this kind of modular covariance, and that determine the gapless boundary. That's how the bulk topological order, how categorical symmetry determine gapless states on the boundary. Okay, so from here, using this ST matrix for the Z2 gauge theory, that's the bulk topological order, we find okay. We find this kind of combination of conformal character using the minimum model transform correctly. This is the one. But actually, we can using this 4-5 minimum model, which central charge 7/10, to have another combination, which also transform correctly. Okay, so it's not uniquely determine gapless states, but determine gapless state to some discrete family, I hope. Yeah. So basically, I think I would, there's some other thing, but this is really the main message. So that there's we have a symmetry. Usually we know that the symmetry would constrain low energy dynamics. And here we say that when you have gapless states, we have a lot of emerging symmetry, and emerging symmetry may have a non-trivial mutual statistics. And these non-trivial mutual statistics correspond to topological order in one higher dimension, which allow us to determine gapless states to a larger degree. Okay, and it's just, but this is just the beginning. This may be a wishful thinking, but I'm hoping we can this picture can be developed further, and maybe a few years, maybe 5 years from now, we have a more complete story, and we know how much we can determine, understand the gapless states from this point of view, or do we need some other ingredients to get a better story? Yeah, thank you very much. Yeah.
So let us thank Professor Wen for the wonderful talk.
Thank you.
Thank you so much. So now we have some time for questions. So questions. I see Gonzalo.
Question? Can I ask a question?
Please.
Yes. So Xiao-Gang. So if I understand correctly, so the gapless, I just want to make sure I understand some of the terminology you mentioned. So gapless means there's no energy gap. Is that
no energy gap?
No energy gap.
But actually, it's much more tricky. That's mean no energy gap in a thermodynamic limit. When you have a finite system, there's always energy gap. But this energy gap level spacing became 0 when the system size getting bigger and bigger. Yeah.
I see. Okay. So you're saying that a gapless case is a difficult case. And my understanding is that you are proposing that for gapless states, there is in mathematics, there's a modular tensor category in some sense to describe that gapless state.
Yes, exactly.
Okay.
And so basically, usually modular tensor category, I don't quite know the audience, so I don't know which language I should use because the two languages are so different. Yeah, indeed.
Yes, yes.
The modular tensor category, people usually study this modular tensor category with relation to fusion category via Dreamfield Center. But also, modular tensor category also studied in the context of conformal field theory. So really, what I'm saying is that I'm really following that line. You know, the conformal field theory also have a modular tensor category in it.
Yes.
And but here I try to view the other way. I feel I have a modular tensor category, and it have a certain boundary, which is conformal field theory. And I try to push that its modular tensor category may determine conformal field theory to some degree. But actually, to be more precise, let me put this following. When you have a conformal field, actually like this conformal field theory. This conformal field theory give you a modular tensor category theory correspond to modular tensor category, which is a quantum double of Z2. Okay. But however, this conformal field theory have an even larger emerging symmetry, have more symmetries. Actually, there is a symmetry of exchanging E and M. Okay. So when I say quantum double for Z2, I did not describe all the emerging symmetry of this conformal field theory. Actually, there's some even more. And so we should include this Z2, E, and M, this EM exchange symmetry. And when we include this EM exchange symmetry, we have an even bigger categorical symmetry. And this bigger categorical symmetry, I don't know whether I mentioned. Yeah, it's here. We call the maximum categorical symmetry, which actually is a double Ising model. So it's a tensor product of Ising and the conjugation Ising model. This is kind of double. We call the double Ising category. Yeah. And this one is better. I think this the critical point of Ising model is really characterized by this double Ising model, which is a maximum categorical symmetry. And from this point of view, although these two theory is a boundary of the same quantum, these two quantum double, but this one have a different emergent symmetry, and their maximum categorical symmetry is bigger for this model. And so from this point of view, we try to propose that each gapless state, each conformal field theory have this maximum categorical symmetry, which correspond to modular tensor category theory. And in this sense, I hope there's a one-to-one correspondence, or almost one-to-one correspondence. And I think this conformal field theory and the modular tensor category, this relation is noticed by mathematicians many years ago. You know, there's this wonderful bigger program in that direction. And I'm describing this in this context really because actually this picture is much bigger and it works in any dimension. In higher dimension, we should have a similar picture. But certainly we have a very little formalism. We cannot do anything, you know. But we hope in higher dimension, we have a similar thing like conformal character in higher dimension. Then we can do this program to study higher dimensional gapless states, which really be revolutionary because that one we really have no clue what to do.
But in high dimensions, even there, I mean, at least in physics, there's the usual ADS CFT holography picture. Is that related or is it something different?
Yes. And so this is a in ADSC holography, it has following thing. They say that if ADS space have a gauge theory, then the boundary would have a G symmetry. Okay, so that's the proposal by these two gentlemen. And however, here we say something a little bit more concrete. That is, we say that if a bulk is a pure gauge theory, I mean gauge theory with a gauge charge but nothing else, then the boundary is a particular critical point, a particular critical theory, CFT. This particular CFT is really the symmetry breaking CFT. So that is the point. So there's this symmetry breaking CFT correspond to a particular ADS bulk, And this particular ATS bulk is a pure G-gate theory.
Mm-hmm.
Yeah.
All
But so this really come to the point. Do we understand the ADF's picture for the pure gauge theory? Just a gravity plus a pure gauge theory, nothing else, no other things. Then this kind of ADS theory should correspond to a particular symmetry breaking CFT on the boundary. So that is the conjecture. You can say that's from our picture I just described. We arrive this kind of conjecture. This pure ADF CFT, a pure gauge theory in ADS space correspond to symmetry breaking CFT in one lower dimension.
Okay. All right. Thank you.
So I think there was one more question by Gonçalo Oliveira. Gonçalo?
I think I was clapping. That was.
Okay. So there is Dmitry Melnikov.
Hi, thank you for a very interesting talk. My question is a naive one. So how is this picture different from, let's say, age mode classification?
Yeah,
in quantum Hall?
It is an edge mode, and however, there is that there we have a topological order in the bulk. Then we determine what is the boundary. Okay. However, I'm using this picture. Okay. So so the emphasize are different. So here, so in this slide, we have a Z2 topological order. We have Z2. We have 2 + 1D Z2 topological order in the bulk. And this particular topological order can have these 2 different boundaries. This is like when you have a quantum Hall states, the quantum Hall state may have different gapless boundary. Okay. And but however, in this talk, I try to consider a different direction. We say, well, we have a gapless system like this critical point of Z2 Ising model. Then we want to find a biggest topological order such that this can be a smallest boundary. There's this thing. You know, we have a fixed topological order in the bulk. You may have a minimal boundary, a larger boundary, like a central charge are different. This central charge is bigger, this central charge is less. You know, you can always add some gapless to the boundary. You can always get a bigger boundary with a more gapless excitation. Okay. And however, but in this talk, I emphasize that when you have a gapless system, we want to discover always emerging symmetry and find the biggest categorical symmetry, or maybe find the biggest topological order, such that this gapless boundary is the minimal boundary of this biggest topological order. And from this, hopefully we can get a 1-to-1 correspondence as much as possible. Otherwise, we don't have 1-to-1 correspondence. You know, a given topological order may have many different gapless boundary. But this minimizing, maximizing may give us a better chance to have 1-to-1 correspondence. So we claim that for every gapless state, there's a maximum categorical symmetry, there's a maximum topological order, which somehow canonical. So this topological order have a minimum boundary is this gapless state you want to study. Then this topological order in the bulk will become a canonical label for this gapless states. And so this is really attempts to understand the gapless state systematically, because we have such a trouble, which is really very close related to this ADF CFT picture. Indeed, there's a very close relation.
Okay, thank you.
So more questions? If not, I have a question. It might. Oh, sorry.
There was a question in the chat from Pasquale Zito.
Yes, indeed.
I couldn't see the chat.
May I ask a simple question? May I ask a simple question?
Yeah, go ahead.
I'm asking the question about the last part, I think.
you show, and you, as I understood that this holographic principle which you proposed, probably 100% is correct. So you extract some information from higher dimension using the studying the physics of boundary. But when we want to very in orthodox form, when we want to talk about ADS safety, I think you need to show that in somehow the conformal symmetry emerge in your theory. In many cases in condensed matter, like for example, the models which is very popular now, this SYK or blah, blah, blah. So in those models, the emergence of the conformal symmetry is verified. I mean, directly you see the conformal symmetry emergence in the some, for example, regimes of the coupling or energy, and then you can describe the correlation function or whatever the partition function using the bulk theory. But maybe I did not understand from this your talk this part that did the conformal symmetry emerge also here? Because I'm not from condensed matter, you know, I came from.
Thank you very much. This is really an excellent question. Let me just
thank you very much.
What in this talk I'm talking about this picture. This is the picture I'm talking about. That means we have a G symmetry breaking transition CFT. We have a CFT coming from the G symmetry breaking transition. Okay, that's in n dimension. And then we say that this can be viewed as a gapless boundary of a gapped state in n+1 dimension. In n+1 dimension, and this gap state is a pure gate theory. A pure gate theory in n+1 dimension have a gapless boundary, which is a G symmetry breaking transition CFT. Okay. However, you can see that this picture and the ADS CFT picture is not quite the same, because as you mentioned that the ADS CFT picture emphasizes conformal invariance, and here we say there's a gapped bulk. This gap have no correlation length. The correlation equal to 0, and there's a gapless boundary. So the picture we have is that you know, this gapless boundary have some boundary region, and that is a scaling region from gaplessness to the gapped bulk. So this ADF CFT picture is a kind of should be inserted into this scaling region, this transition region from gapless boundary to gapped bulk. Or another way to say that if we combine these two pictures, we get this picture that in the ADS space we have this scaling region. But then, you know, in ADS, you can go to infinity in the radial direction. And what we say is that this infinity is a pure gauge theory or topological order in n+1 dimension. So our picture in my talk, we did not talk about this transition region or scaling region. We just talk about this relation between this gapless CFT and the bulk topological order. It's already gapped, no scaling here. Here already have no scaling. And then, so ADF CFT just happened very naturally, just insert in the middle. So that's why we feel this may be a right picture. So our picture describing two extreme points, and ADS space happen to describe how these two regions transition to each other. And because we know the infinity is a pure gauge theory, so that's why we conjecture that maybe this ADS space have only pure gauge theory. This is a particular ADS theory with a pure gauge theory would describe this G symmetry breaking CFT. That is a rationale. Yeah.
Thank you very much. Thank you.
Is there time for one more question?
It seems there's one more question by Deepak Vaid.
Hello, Professor Wen. So the picture that you are pointing out, so it seems to me that one way to understand it is that you have the conformal field theory, then the transition region consisting of the ADS space.
Yes.
And then the pure gauge theory, the middle part of the three diagrams, that would correspond to something like the interior of a black hole. So if you have like an ADS space-time with a black hole embedded in it. So this would.
I don't count actually. This limiting point may be a black hole, but this black hole may have a very small size because this is zero temperature equal to 0. So you may feel this infinity point at infinity in the radial direction is a point black hole. But here I want to say that this point black hole have structures. This structure is a pure gauge theory. It's a topological quantum field theory. It's a TQFT.
Right.
And yeah, this is what we try to say that, usually people say at infinity, we just ignore them. But here I say this infinity is a TQFT, have a structure. And this structure, in some sense, determine what the middle should looks like. Yeah, so basically, there's conformal field theory, there's TQFT, we are talking about TQFT, and the middle is ADS theory, yeah.
Well, you do have extremal black holes which have 0 temperature horizon, if I'm not mistaken.
Yeah, this is more like an extremal black hole, I say. So yeah, right. In some sense, yeah, it's a black hole with no entropy,
right?
Or with no thermodynamic entropy. May have a finite entropy. I mean, a few degree freedom.
Okay. All right. Thank you.
So as Roger was saying, there is a question in the chat by Pascual Zito that says the following: quantum doubles, if I understand correctly, imply central charge equals to 1. How does central charge equals to 1/2 in the Ising CFT appear in your framework?
Yeah, thank you. Central charge equal to 1. Maybe that's a multiplicative central charge, and in physics we say 0. That's so central charge should be equal to 0. So quantum double central charge equal to 0. But however, I should say that the total central charge equal to 0. Here I have a C and a C bar. So total central charge is equal to C minus C bar. So the right mover, left mover, this holomorphic part, anti-holomorphic part, and they are the same, they cancel. So this equal to 0. So that's just fit. And but there are topological order with a central charge not equal to 0. And their boundary, C and C bar will not equal. Will be different. That's a chiral boundary.
So any more questions? Pascual, thank you, by the way. So I have maybe one question. If you still have strength, this was quite a session of questions.
No problem.
So in the previous slides, I think the previous one before this, you have this set of transformation rules for these ZIs, right? So it seems like you're kind of defining a vector bundle over the moduli space of complex structures on a torus. And it seems that these are simply flat multipliers. So basically, you're maybe trying to classify in class of vector bundles over this moduli space.
Yes, exactly. So actually, this modular space has some flat connections, and so those are holonomy. Those are holonomies. Yeah, that's another way to look at it. Basically, this vector bundle is this upper half plane, and those module transformation identify certain upper half plane, certain point on the upper half plane to be equivalent, and so they are related by this ST transformation. Yeah. So indeed, that's another thing. That is so more generally we can say that topological order is a degenerate ground state, but however we can deform our Hamiltonian and the ground state inertia remain to be the same. The space of a deformation of Hamiltonian is a modular space. And then for every Hamiltonian, we have degenerate ground state, that's a vector. So therefore, the degenerate ground state gave us a vector bundle on this modular space of a deformation of Hamiltonian. And this is the general point of view for any topological order in any dimension. So the topological data we talk about is really the vector bundle. It is a vector bundle on the modular space of a deformed Hamiltonian. and
see,
that is a better way, more general way, not using this ST matrix. Yeah. And so maybe I should using this more mathematical language to describe it. I'm using pretty physical language for this talk.
No, it's great. It's quite interesting because here you're describing interacting topological phases, right? Not in the sense of SPTs.
No, yeah,
but, yeah,
these
also
are all
in
interacting.
SP, right, but in SPTs, I mean, at least we are familiar with these vector bundles, these block bundles of occupied states in the Brillouin zone. So in some sense, this vector bundle, they just appear in different spaces, and they appear everywhere where there's this.
Exactly. So in a non-interacting system, we have a single body Hamiltonian. The Brillouin zone is a space of a single particle Hamiltonian, and we have vector bundle there. Here we consider many body Hamiltonian in a Hilbert space of a 2 to the 10 to the 23 dimension. And the bracket is here. That's make it even bigger. And so, but there's a 3-dimensional, 4-dimensional subspace of this huge space. And this vector may move around and give us a vector bundle of a space of a many body Hamiltonian. And this vector bundle in a space of a many body Hamiltonian is a key to understand topological order. And we believe this vector bundle encode all the information for topological order. But this kind of study is a few, certainly not every vector bundle is allowed. So we have to say which vector bundle is realizable by local many body Hamiltonian. And this is a big question.